Imagine changing the sound of your voice into light pulses and sending it over a single hair-thin glass filament with thousands of other voices. Well, today, tiny strands of incredibly pure glass carry voice, data, and video transmissions all at the same time, all over the world. We call these glass fibers light guides. AT&T Network Systems in Georgia produces large quantities of several different types of low-cost, high-quality light guide cable. Before examining the manufacturing process, however, let's take a quick look at the three common types of light guide fiber. These are multi-mode fiber, enhanced fiber, and single-mode fiber. Standard multi-mode graded index fiber is used in commercial systems which communicate at 90 million bits per second over distances of 6 miles without repeaters. It's been designed to operate with microscopic laser light sources and has a 50-micron diameter core with a total outside diameter of 125 microns. By comparison, a human hair has a diameter of about 100 microns. The core region, that portion of the fiber which actually conducts light, has a graduated refractive index profile. Since light may enter the core from a variety of angles, this graded index profile permits the fiber to function like a lens. Light traveling down different paths or modes is gently guided to repeated points of convergence as it tries to spread out. The graded index, therefore, reduces dispersion, allowing multimode fiber to provide a good information-carrying capacity over moderate distances. Enhanced multimode fiber, while similar to standard fiber, has a different size core to capture the maximum amount of light from light-emitting diode sources found in the subscriber loop or slick environment. Enhanced fiber has the same outside diameter as standard fiber, 125 microns, but a larger 62.5 micron diameter core. It may be used in systems transmitting 45 million bits per second over distances in excess of 11 miles. The newest development is single-mode fiber, which has an 8-micron diameter core. The principle here is to reduce the core to a size so small that only a single mode of light may be conducted through the core. Using this technique, engineers have demonstrated error-free transmission of more than 400 million bits per second over distances in excess of 40 miles without repeaters. Even higher bit rates and distances are achievable. Basically, manufacturing light guide cable consists of 6 processes. Producing an initial preform, which is a large glass rod with good optical properties. Heating this preform and then drawing fiber from it, similar to pulling taffy. Measuring and grading the fiber to determine its physical and optical properties. Assembling the fiber into units, either ribbons or stranded. Cabling the units with a variety of protective materials. And finally, installing any appropriate connectors to the cable ends. In step number 1, the preform begins as a hollow, 4.5-foot long tube of quartz glass about the diameter of a quarter. This glass is so pure that it makes eyeglass lenses seem opaque by comparison. First, it is carefully inspected, cleaned, and tested to verify its purity and dimensional characteristics. Next, AT&T Network Systems uses the Modified Chemical Vapor Deposition, or MCVD process, to deposit layers of glass on the inside wall of the tube. The 3 components of an MCVD system include a glass-working lathe, a chemical delivery system, and a control computer. The lathe supports and rotates the silica tube, while a motor-driven oxygen-hydrogen torch slowly moves along the tube's length. An optical heat sensor is constantly monitoring the torch's hot zone temperature. This information is used by the computer to adjust the torch temperature and speed, and route chemicals from the chemical delivery system through the rotating hollow tube. After the hollow quartz tube begins to rotate and the torch is ignited, a mixture of gases including germanium tetrachloride, silicon tetrachloride, and oxygen is passed through the center, causing silica particles to be deposited on the tube wall downstream of the torch hot zone. These particles are then fused into a uniform layer of glass as the torch gradually traverses the tube's length. It may make upwards of 50 passes. This procedure is repeated layer after layer until the required thickness of glass is obtained. Some of these glass layers will eventually become the fiber core we discussed earlier. For multi-mode light guide preforms, the mixture of gases is changed slightly during every pass so that each layer deposited has a slightly different density and index of refraction. For single-mode preforms, over 90% of the passes are for additional cladding material around the core. In the final stage of the preform process, the torch is allowed to make several slow passes as its temperature is increased to over 1900 degrees centigrade. As the glass softens, surface tension causes the tube to collapse, forming a solid preform rod about 3/4 of an inch in diameter. On the left is a completed preform ready for step number 2, drawing light guide fiber. But first notice in this cross-sectional close-up that we can actually distinguish the various layers of glass which were deposited during the MCVD process. The strength of a newly drawn fiber, its dimensional accuracy, and its surface condition all depend upon the drawing process. AT&T Network Systems draws light guide fiber using computer-controlled drawing towers. First, a solid preform, which has already been quality inspected, is vertically mounted to a motor-driven feed mechanism. This preform is then slowly lowered into an induction furnace whose temperature is closely monitored by a computer. In a few minutes, when the preform's tip is heated above its softening temperature, a technician can begin to pull fiber from below the furnace. Its diameter is being constantly monitored with a laser micrometer. The computer compares this information with a desired diameter and automatically adjusts the drawing pull rate once the fiber has been properly routed to a take-up spool. A light guide's diameter must never vary more than 1% over its entire length. As we will see later, this helps minimize transmission losses at connector points. Once the diameter has been checked, 2 protective coatings are immediately applied and cured. The first coat is a soft plastic polymer which protects the fiber's fresh surface, while the outer layer is harder and more rigid for abrasion resistance. This coating process is critical. It prevents contamination and surface damage to the fiber while maintaining light guide's intrinsic high strength. Finally, the freshly coated fiber passes over a drawing capstan, which has been controlling the entire pulling process, and loosely wound onto lightweight plastic take-up spools. One preform has yielded over 10 kilometers of light guide fiber. The fiber's cross-section, although considerably smaller, faithfully duplicates the layered structure of the original preform. As a last step in the drawing operation, every section of fiber is proof tested for strength. This might range from 50,000 pounds per square inch for standard multi-mode fiber on up to 200,000 pounds per square inch for single-mode fiber laid on the ocean floor. The light guide must be able to withstand the stress of manufacture, installation, and of course service. Although accurate physical and optical measurements are conducted on every preform, it's absolutely essential before proceeding further that the exact transmission properties of the light guide fiber be verified and documented. 4 tests have been developed which accurately evaluate the performance of light guide fiber. They measure a fiber's physical dimensions, its spectral loss, bandwidth, and index of refraction. Let's look at the importance of each test. Any mismatch in core cross-sections when light guide fibers are spliced causes a loss of optical power and a reduction in the fiber's information carrying capacity. Therefore, a light guide fiber's physical dimensions must be carefully verified. Not only should the dimensions be precise, but the core and cladding must be concentric and round, as illustrated here. The second test is designed to measure fiber loss, which is the decrease in the intensity of light as it travels down a light guide's core. An optical loss test set is used to measure fiber loss over 6 different spectral frequencies. This graphic shows how light may either be scattered by geometrical imperfections or absorbed by material impurities. Test number 3 measures the light guide's bandwidth, which may be defined as the bit rate or information carrying capacity of a light guide fiber. The more information carried per fiber, the more economical the light wave system. This test is conducted using 2 different light wavelengths. Finally, test number 4 evaluates the graded index profile of standard or enhanced multi-mode fiber. Since the graded index is controlled during the preform step, these test results will provide valuable manufacturing feedback for the modified chemical deposition process. As we mentioned earlier, the graded index ensures that light waves can travel long distances without regeneration by minimizing dispersion and preserving bandwidth. After each test has been completed, the results are preserved on magnetic data cassettes and paper tape printouts which accompany each spool of fiber. The fiber is graded using performance designators and stored in an inventory library. Step 4 in the light guide manufacturing process is to assemble the light guide fibers into units, either ribbon or stranded units. Fiber is chosen to be of the quality desired or better, based upon its length and transmission characteristics. First, let's talk about light guide ribbons, which are 12 fibers laying side by side, sandwiched between two layers of adhesive mylar. There are 4 stages in the ribbon manufacturing process: fiber payout, organizing the fibers, laminating the fibers with mylar, and take-up. The payout section may accommodate up to 12 spools of fiber selected from inventory. Under controlled tension, these are fed through a 12-position organizer, which keeps the fibers in proper orientation. At this point, the fibers also are color-coded for future identification. The fibers then pass through a geometric organizer, which positions the fibers into a flat, closely spaced arrangement. In the laminator, adhesive mylar is fed from upper and lower spools around a set of laminating rolls. For identification and durability, length and grade markings are permanently printed on the inside of the adhesive tape. As you can see, the laminating rolls sandwich the 12 light guide fibers between 2 layers of mylar tape. Any excess mylar is trimmed from the ribbon sides, and it's passed through an optical viewing station for inspection. Finally, the ribbons are taken up onto spools and tested for optical loss to verify that nothing has changed. We'll return to ribbon units in a moment, but now let's take a quick look at the difference in a stranded unit. You'll notice in this cross-section that a typical stranded unit effectively packages up to 16 separate light guide fibers. The fibers are first color-coded for identification and then wrapped around a single strength member and buffer layer. Finally, the stranded unit is protected by a layer of flexible gel and an outer tube. Now that the light guide fiber has been packaged into either multi-fiber ribbon or stranded units, it's time to decide on a cabling scheme which will protect it from abrasion, stress, and temperature or moisture extremes. We'll be illustrating the differences between multi-fiber ribbon cable, multi-fiber stranded cable, and single-fiber cable. Multi-fiber ribbon cable may contain up to 144 light guide fibers by stacking up to 12 multi-fiber ribbons. Typically, these ribbons are then protected with an inner polyethylene tube, followed by 2 protective layers, each composed of a heat protective wrap, steel or non-metallic strength members, and an outer polyethylene coating. In fact, ribbon cable may be manufactured with a variety of protective jackets, depending upon the anticipated service environment. There's gel-filled waterproof cable, rodent-protected cable, flame-retardant cable, even double-wire armored cable. Steel strength members may be replaced with non-metallic strength members, and copper wire pairs may be included for talk circuits to be used during the installation phase. Since it may be interesting to see how these cables are actually manufactured, let's take a brief look at the multi-ribbon cabling line. First, up to 12 spools of light guide ribbon are installed at a rotating drum. The ribbons are paid off and stacked, and the stack is given a slight twist or lay. This core of ribbons is then fed into an extruder, which forms a protective jacket of polyethylene. The jacket's diameter is immediately sized to its proper diameter in a pressurized water trough. This is followed by an application of stainless steel or non-metallic strength members, which are spirally wrapped around the tube. The cable then enters the intermediate jacket extruder and passes through a cooling trough. To enhance the strength of the cable, a bedding layer is applied and a second set of strength members is added. Notice that the second set of strength members is applied in an opposite lay from the first set. This technique minimizes any twisting forces in the finished cable. Finally, another pressure extruded jacket is added, and its diameter and length are measured. The finished cable, about a ½ inch in diameter, is then wound onto small steel reels which are painted blue to distinguish them from standard cable reels. Notice from this illustration that the stranded unit is cabled using the same basic materials. Essentially, a stranded unit is protected with two separate bedding and strength member layers, followed by an outer polyethylene sheath. Besides the single unit stranded cable, it's also possible to manufacture a cable containing 3 separate stranded units as shown here, or a cable containing 6 stranded fiber units with steel or non-metallic reinforcement. The third type of cable is single fiber cable, which usually serves as jumpers for central office equipment between cables and regenerators and its data links. Because strength is the most critical concern with single fiber cable, high-strength filaments are used between 2 layers of PVC plastic. This offers both mechanical and environmental protection. As a final step in the cabling process, a short section of outer sheath is removed from each end of the cable, exposing the multi-fiber ribbon units. Sheath terminating hardware is installed, and the cable is then ready for step 6, connectorization. As illustrated here, the problems encountered when designing light guide connectors include axial misalignment in the upper left-hand corner, angular misalignment in the lower right-hand corner, and the separation distance between the fiber ends in the lower left-hand corner. All of these conditions will increase the amount of optical loss across a connection. A properly aligned and spaced light guide connection is shown in the upper right-hand corner. Let's look at two different types of light guide connectors which have been developed to minimize these problems: the single fiber biconical connector and the multi-fiber ribbon array connector. First, let's examine the biconical connector, which is used primarily on light guide patch cords and jumper cables. The components include two plastic conical plugs at the ends of the fibers we wish to join, and a biconical sleeve, which accepts and properly aligns the plugs. The biconical sleeve is precisely molded from epoxy resin, while the conical plugs are molded directly around the single fiber cable. This technique automatically centers the light guides into each plug. During manufacture, the conical plug length is sized for proper fiber separation when connected to the sleeve, and its end is polished to an optically smooth surface. Finally, each connector is microscopically inspected and tested for optical loss. Although similar in principle, the array connector uses an etched silicon chip designed specifically for the 12-fiber ribbon. A single multi-fiber ribbon splice is made by removing a portion of the mylar tape and fiber coating from the end of the ribbon and permanently affixing two etched silicon chips. Since these chips have been specifically designed to be used with multi-fiber ribbons, they consistently and accurately align all 12 fibers. These silicon chips are referred to as being positive chips. A simple butt splice is completed out in the field by using two negative chips, which mate with the positive chips, and then injecting an index matching gel between the chips to avoid any signal loss. Small metal clips hold the entire assembly together. This arrangement provides the precise end-to-end fiber alignment necessary for good optical connections. Now that we've completed the 6 basic manufacturing steps, each light wave cable is routed to final inspection, where its transmission characteristics are again measured and verified. On a sample basis, every element of cable may be examined and analyzed as part of a total quality assurance plan. This extra care helps guarantee that the light guide fibers are protected against physical damage and moisture, not only during initial installation, but throughout its service life. Prior to shipment, the connectorized ends are covered with protective hardware and pulling eyes, and protective membranes are wrapped around each reel. At last, the light wave cable is ready for shipment, and because of its light weight, typically 80 pounds per 1,000 feet, light guide cable may be sent air express. As we've just seen, making light guide cable has required the development of manufacturing processes unlike any which have existed before. Last year's wonder has become today's routine, using the world's purest glass to economically meet customer service needs, now and in the future.